Hello, this is Jack Jackson. I'm going to be using my classification and properties of quadrilaterals GeoGebra app that I have here. Remember earlier a couple playlists back, we looked at what happens when we have a quadrilateral and you draw one of the diagonals and you get some congruent triangles. And we found that that's a couple basic categories. If ABC is congruent to uh, um, if ABC is congruent to ADC, we get a kite. If ABC is congruent to CDA, you get a parallelogram. But there's actually 6 ways you could get triangle ABC congruent to ADC by the 6 different orders we could put here. If ABC is congruent to ACD, we get a special kind of kite where one of the major diagonal is congruent to 2 of the sides. And the same thing happens if you get ABC congruent to DAC. If you have ABC congruent to DCA, you get a parallelogram, but a special kind of one where one of the diagonals is congruent to the 2 sides. Same thing happens if you have ABC congruent to CAD. And if you have ABC congruent to ADC and ABC is congruent to CDA, you get a rhombus. And if you get, there's a special one here where it's basically made up of 2 equilateral triangles where a diagonal is congruent or to all the sides there of a rhombus. And there's several conditions there that give you that. So that's kind of an interesting thing that you can get for some congruent triangles. We looked at that earlier. I want to look now at what happens if we have some similar triangles. Okay, so first of all, I'm going to take a diagonal and the sides like we just did. Well, the first one is this situation here. If you take the diagonal here and the sides, okay, okay, so let's look at the angles here. So if these are similar triangles, we know all of these angles are congruent. And since side AC is corresponding to AC with this setup, see AC and AC, then these sides are proportional and the proportionality constant must be 1, therefore these must be congruent. We've already seen that that's enough to make that a kite. Okay. Okay, so here we have the figure. There's the diagonal, there are the angles. So if we're assuming that we have similar triangles, all the marked angles have to be congruent. The red ones with the 3 marks have to be congruent and so forth. Well, if you look here, again, AC is going to correspond to CA the way this we're doing. ABC is similar to CDA. You got A first and last, AC or CA is similar to or corresponds to AC. So we know the proportionality constant has to be 1 between these 2 similar triangles. Therefore, these are actually congruent triangles, and we have a parallelogram as we've looked at before. All right, we got a couple more classes. What if, so there's actually 6 possibilities to take ABC similar to this triangle with vertices A, C, and D. There's 6 different orders for the second triangle to match these up, 3 different correspondences. So here's one. ABC is similar to CAD. Now this one looks like this. So here's A, B, C, and it's similar to CAD. So let's look at this. A and C in the second one has to be the same measure as A in the first one. So C down here has to be like A up here. So those are the 2 red ones. Okay, A in the second one has to be the same size as B in the first one. So A in the second one, that's the green one here, and B in the first one. Those 2 green ones have to be similar, or congruent angles. Okay, because the 2 triangles are similar. And then that finally makes the other pair, the blue ones, congruent as well. Well, if you look at it right here, if you look at these two consecutive angles, this central angle at A, I mean the not central angle, but the interior angle at A, the big angle, that's angle BAD. It's made out of the red one and the green one together. And then we have a blue one down here. Well, if you look at this, red, green, and blue are going to always add up to pi radians or 180 degrees. Okay, and so we see that these angles here, the big angle at A, that is the angle BAD, and the angle CDA are supplementary. That makes this a trapezoid. Of course, you get the same relationship on this other end. This time it's the blue and the red together, plus the green up here. So these are similar triangles. Not congruent, as you can see this time. So this time, whatever your proportionality constant is, let's see, we take side AB from the first one. CA is going to correspond to that in the second one. So whatever your proportionality constant is, multiply, in this case, the 15.18 by whatever that K is to get the 11.25. Okay, we'll multiply by 11.25 over 15.18. And then that same fraction, that same K, you're going to multiply by that length to get this length down here at CD because, where are we? Okay, because in the first triangle, AC, that's the first and last ones here, has to correspond to the first and last here, CD here. And we get that. And of course, the same proportionality constant is going to give you the relationship between the side CB and the side AD. So that's kind of interesting. It's a special subclass of trapezoid. And this other one really is the same thing. It's just basically the labels of A and C are just swapped, but you get the same basic relationship uh, here. Okay, so those are the two. Basically, this is the same setup. Let me show you how A and C, it's just sort of, if you put the B up here and the D down here, that is basically just swapping the labels on A and C here. Otherwise, they look the same thing. So those are the same class. Finally, there's one final. So that was a subclass of trapezoids, not just any trapezoid, because trapezoids in general don't have necessarily similar triangles here. So it's a special kind of trapezoid, not one of our normal special kinds of trapezoids, not necessarily a parallelogram, not necessarily isosceles, not necessarily, a rectangle or right trapezoid or any of those special kinds of trapezoids, but it is a special kind of trapezoid, okay, with an extra property. Okay, now this up here was just any old kite, has that, any old parallelogram. Special kind of trapezoids here and here. And finally, we got two others that turn out to give us the same class. I'll go ahead and pull them both up here. The first one is ABC is similar to ACD. So A has the same size in both of them. So that means you've got an angle bisector up here at A. See how those are both 11 or 1.11 radians? Okay, so at A, your diagonal here is an angle bisector on this end, but not necessarily on the other end, as you can see. So, kite has that possibility where we have an angle bisector there. And I guess there's a place somewhere in here where we could, if we get this just right, we could make this into a kite, but it's not necessarily a kite, right? But you do get an angle bisector on this end, maybe or maybe not on the other end. You don't necessarily have any parallel sides here. As you can see, for example, there, pretty clearly that none of those are parallel. So it's not necessarily a trapezoid or a parallelogram or kite, and not any of our standard kinds, but you do get something interesting there, that you do get an angle bisector here, and you do end up getting the two triangles similar to each other. And you get exactly the same relationship down here. It's basically just this same picture with the A and the C. Let's see, the sort of the labels are swapped. So at this time uh, the angle bisector is at C rather than A. Okay, so it's still basically the same kind of thing. So there's another special kind of quadrilateral, but it's not one of our our usual suspects, not one of our standard kinds. So there's another way to look uh, at quadrilaterals that way. Now, continuing on this idea of looking at similar triangles, there's another way we could get some triangles. Okay, so let's say we have a let's say we've got a quadrilateral like this, and we draw both diagonals, and they meet at a point, let's call it X. There's 4 little triangles made here. Well, some of those might be similar, okay? So here's a case where I've marked at least 2 of the angles uh, matched up. Actually, I've marked all 3 of them. So you have vertical angles that are congruent here. This angle and this angle up here are congruent. And then this one and this one are congruent. Well, since this one and this one are congruent, that's from our Z property tells us that this has to be, these 2 lines have to be parallel. Alternate interior angles are incongruent there when we have, think of the top and bottom lines as being your lines will end up being parallel. And this is your transversal, goes through B, and I guess we need to call this guy D. Okay, of course the other ones down here gives you the same thing. Your Z's going like the normal Z order, and then you got this angle at A and this one down here at C are congruent. Again, another pair of alternate interiors. Again, that gives you the same lines parallel. Not necessarily a parallelogram. And notice that the triangles that are left, the one here, AXD and BXC, not congruent, not similar necessarily. So. But it turns out to be if you get these similar, this has to be a trapezoid, and of course if you get a trapezoid, they have to be similar, because if you get a trapezoid, then again the Z property the other direction tells us that the 2 red ones are congruent, the 2 blue ones are congruent. Vertical angles are always congruent, so that they definitely have to be similar. Okay, another possibility is this one here on cyclic quadrilaterals. They have some similar triangles as well. So look what happens here. Using the inscribed angle theorem, you can see that this red angle at B, that is ABD, and the one ACD, both intercept the same angle, and they're inscribed angles, so they have to be congruent. Of course, vertical angle pairs are congruent here at X. And then this angle, the purple one I've got marked here, CBD, and a purple one here, CAD, they have to be congruent as well. It's purple one here. Right now, 0.76 radians, the way I've got it drawn at the moment. And similarly, the green one here, BDA and BCA, they intercept the same chord, so same arc. So they have to be congruent as well. And so we see we got some similar triangles here. This one here, BXC, is similar to AXD. And so this one in here and this one here, not necessarily congruent, as you can see, but similar. And then again, not necessarily congruent, but similar are these 2 here, AXB and, gotta get the order right, DXC. So 2 pair of similar triangles. If you get the 2 pairs of similar triangles like we see here, then we can get this to be cyclic like this. So it's an if and only if. Let's see how we do it. Let's see. So we got a pair here and a pair here. And so all of the colored angles matched up are congruent. And let's see. Okay, so if you look at what we've got, not counting the ones around X, if you look at the other ones, what do we have? We've got a blue, a purple, and a green, and a red. Blue, purple, green, red. We have 4 different colors. And if you look, we have 2 of each at the 4 corners. Okay? So if you add all those together, what do you get? well, you're going to get 2 pi, or 360 degrees, which you always get for a quadrilateral. But if you add one of each color, the blue, purple, green, and red, then you add all those together, you got to get half of the total, so that has to be supplementary, and we get opposite angles supplementary and opposite angles supplementary here, and we know we've already proved that's enough to make it a cyclic quadrilateral. So that's kind of interesting. Um, if you get, here are the angles there, so if you get these corresponding ones here to be congruent angles, what we get a parallelogram this time. So let's see what we're looking at here. Okay, we're looking at ABX similar to CDX. So A to B to X. So this one over here and this one over here. C to D to X. So then they've got a corresponding one here, the blue one and the blue one here. Well, that gives you a Z going this way. So these are alternate interior angles. If you think of the diagonal as being the transversal, that makes this side and this side parallel, the two blue angles being congruent. And the two red angles being congruent, that gives you your Z going this way, sort of a backwards Z, and that gives you the alternate interior angles to this one being congruent. So those two have to be parallel. So now it makes it a parallelogram. Okay. And one thing we notice, once you get that it's a parallelogram, then you know a little bit more. You know that a parallelogram, they bisect each other on the diagonals. So in fact, this distance from B to X and from D to X has to be the same distance. Therefore, the proportionality constant is 1, and these are actually congruent triangles across here and across here. And of course, if you start with parallelogram, we've already proved that those little triangles are congruent, so that takes care of that. Next, if we have some similar triangles this way, so this one works out to be an isosceles trapezoid. Let's start with an isosceles trapezoid and see what we've got in way of similar triangles. Well, we actually have, of the 4 little triangles here, we've got one pair that's actually congruent. We've got these legs are congruent here. We know this about these. Because of the Z property, we have a Z here. So we got this green one down here is congruent to that green one up there. This one here, up there, congruent and so forth. The thing that's maybe not completely obvious at first is that not only are these congruent across this way from the Z property, that we also get, we can prove that the triangle, and we did this earlier, that the triangle CAD is congruent to the triangle DBC, making the two red angles congruent. Okay, and you're given that the big angle, blue plus green here, the big angle DADC is congruent to angle BCD. And so that turns out to be enough to get all the corresponding angles that you got congruent, and also makes these two triangles here isosceles. And it also turns out, because these are congruent legs with those two triangles congruent that we talked about, that means that the proportionality constant on these two triangles right here, BXC and AXD, they're actually congruent. Okay, proportionality constant is 1. But when we go across here, AXB and DXC are similar triangles, and they're both isosceles. So you could either say ABX or BAX, and you could say C dx or dcx, either way you want to say it. But those aren't necessarily congruent. Okay. So what if you get so if you get ABX is similar to CDX. So starting with the similar triangles, ABX similar to CDX, then you get these angles matching up like we said here. And then if you've got but not necessarily the two green ones the same. And then if you say it's also similar to DCX, if CDX is similar to DCX, then that has to be an isosceles triangle because you're just saying that these angles are congruent. We already know that's enough to make that an isosceles triangle. So that gets you the isosceles triangle part here. Okay, and then that's enough to make this distance from A to X the same as the distance from B to X, and this distance down here the same as that, and you got vertical angles congruent, so that makes this triangle over here and this one over here congruent as well. That's automatic, right? And so that's enough to make this an isosceles triangle, I mean isosceles trapezoid. So some interesting relationships there among the different little triangles that are formed here uh, and here with some similar triangles. Same for that one there, and then the ones with we had some similar triangles just looking at one diagonal. Some similar triangles there, actually congruent ones there, similar ones here, here, and here, and here. So lots of cool, interesting things to look at there with similar triangles and congruent triangles for uh, quadrilaterals. Kind of interesting.